Lesson 11, Magnetic Fields. Part 1, Introduction to Magnetism. When we were studying charges, we learned that charges come in positive and negative. A magnet is made up of a north pole and a south pole. You can't have an isolated north or south pole. Unlike charges, which come in separates, north and south poles always come together. So if you have a magnet and you try to cut it in half with a knife, or I'm going to draw a pair of scissors trying to cut it in half, you actually end up with two smaller magnets instead of two separate north and south poles. A magnet cut in half becomes two separate magnets. Magnetic forces. The magnetic force is attractive for unlike poles. So if you have a south and north pole of a magnet near each other, they will be attracted to each other. Magnetic force is repulsive for like poles. So if you have a south pole and a south pole near each other, they will be repelled. And if you have a north and a north pole near each other, the force will try to push them apart. Magnetic forces are action at a distance forces, like electric and gravitational forces. Because of this, they can be explained by magnetic fields. A magnetic pole in a magnetic field will always experience a force. This force will be attractive or repulsive depending on the type of pole. The direction of the magnetic field is the direction that a north pole would experience in that field. North poles will be attracted towards south and away from north. The direction of the magnetic field is also the direction that a compass needle would point if it was placed in that field. The compass needle will point towards south. Here's some examples of magnetic field lines that you're going to need to be able to reproduce on tests. If you have a single bar magnet, you'll see that the lines will always point at the south pole of the magnet and away from the north pole of the magnet. If you have two south poles of two separate bar magnets facing each other, the magnetic field lines will point towards each south pole, similar to how the electric field lines point when they're directed towards two negative charges next to each other. There'll be a neutral point in the middle where the magnetic field lines oppose each other and cancel each other out. If you have two north poles of bar magnets near each other, the magnetic field lines point away from each north pole with a similar neutral point in the center. This looks similar to when you have two positive charges with the electric field lines pointing away from the positive charges. If you have a north and south pole pointing towards each other, it looks similar to when you have a positive and a negative charge placed next to each other. The magnetic field lines point from the north pole to the south pole. So far, we've learned about gravitational, electric, and magnetic fields. They all have different sources. Gravitational fields are caused by masses. Electric fields are caused by positive and negative charges. And magnetic fields come from north and south poles. The symbol for gravitational field is small letter G. The symbol for electric fields is capital E. And the symbol for magnetic field is B. And since magnetic fields are vectors, we put a little arrow over top of the B to indicate that it's a vector field. The unit for gravitational fields are either the Newton per kilogram, or we write this as meter per second squared, which is the equivalent unit. The unit for electric fields is the Newton per coulomb, or the equivalent unit, volt per meter. The unit for magnetic field is capital T, which stands for the Tesla. The direction for gravitational field is always towards whatever mass is causing it, and it points at the center. Electric fields point towards negative charges and away from positive charges. And magnetic fields point towards south and away from north. Earth's magnetic field. The Earth is like a giant bar magnet. No matter where you stand on Earth, the needle of a compass will be attracted towards the North Pole of the Earth. We can sketch in the magnetic field lines because magnetic field lines always point in the direction that a compass points. So in this case, our compass points from the South Pole of the Earth to the North Pole. The problem with this is we know that magnetic field lines always point at south and away from north. And we also know that the compass needle will point in the direction of magnetic field it points at south. This indicates that the North Pole of the Earth is actually a magnetic south pole. So if you were to imagine the bar magnet that is the Earth, the south pole of the bar magnet is at the North Pole of the Earth, and the North Pole of the magnet is at the South Pole of the Earth. Part 2. Induced magnetic fields in wires. In 1820, Hans Christian Ørsted discovered the link between electricity and magnetism during a lecture. He set up a wire carrying electric current and noticed that the compass needle moved when the current was turned on and off. This was a very major discovery in the field of electromagnetism. Ørsted's discovery was that moving charges produce magnetic fields. Moving charges is another way of saying electric current, or changing electric fields produce magnetic fields. Now, in our study of magnetism, we're going to use a series of hand rules to determine the direction of vectors. Before we get in depth about these hand rules, there's a couple guidelines we need to go through. If we're using our left hand for the hand rule, we're using it for the flow of negative charges. This is for electron flow. If we're using our right hand, we're using it for the flow of positive charges. Now, we know that positive charges can't actually move. Protons are stuck in the nucleus. So when we refer to the flow of positive charges, we're referring to something in electricity referred to as conventional current. Electrons flow from the negative terminal of a battery to the positive terminal. This is the true flow of current through a wire. The concept of conventional current, on the other hand, was developed before the discovery of the electron. Before the electron was discovered, it was thought that positives flowed through wire, and as a result, conventional current is something that flows from the positive to the negative terminal of the wire. Now, we know conventional current doesn't actually exist. It's really electrons that are flowing through the wire. Conventional current is the imaginary flow of positives from the positive terminal of the battery to the negative terminal of the battery. Now, for tradition's sake, conventional current is still used in electronics today. Now that you understand a little bit about which hand to use and the difference between electron flow and conventional current, you're ready for the first hand rule. The first hand rule is used to determine the direction of the magnetic field around a wire carrying a current. For the first hand rule, you point your thumb in the direction of the current through the wire. And then you wrap your fingers around the wire, and your fingers wrap in the direction of the magnetic field. So point your thumb in the current direction. If the current is the flow of electrons, you use your left hand. If the current is the flow of conventional current, which is the flow of imaginary positives, you use your right hand. It will tell you in the problem which kind of current you're talking about. You curl your fingers in the direction of the magnetic field. So there you imagine little arrows coming out of your fingertip, pointing in the direction of the magnetic field. Here's an example. In this example, the current flowing through the wire is represented by electron flow. This means that we know to use our left hand for the hand rule. We point our thumb in the direction of the current flow, and this means that the magnetic field wraps around the wire in the direction of our fingers. This allows us to draw in the looped path of the magnetic field lines. If the current were conventional current instead of electron flow, we would use our right hand. Again, we would point our thumb in the direction of the current flow, and our fingers wrap around the wire in the direction of the magnetic field. And the magnetic field loops around the wire in the other direction if the current is conventional. For our second example, we've placed a compass on top of the wire. And we want to know which direction does the compass needle point. Since we're using electron flow, we know to use our left hand for the hand rule. So we point our thumb in the direction of the current flow, and our fingers wrap in the direction of the magnetic field. Now, in front of the wire, our fingers wrap towards the right. So we know the compass needle points to the right when it's on top of the wire. But the magnetic field wraps around the wire. And behind the wire, our fingers move to the left. So we know behind the wire, the magnetic field will be to the left. In the past, we used vector directions such as up, down, left, and right. But since magnetic fields are three-dimensional, we need two more vector directions. These are into the page and out of the page. If an arrow disappears into the page, it will look like an X. So when you see an X for a vector symbol, that means the vector points into the page. If the vector is coming out of the page, it will look like the tip of an arrow coming towards you, or a dot. So if you see a dot for a vector symbol or a vector line, that means the vector is coming out of the page. For example, and in this example we use electron flow, so we know to use the left hand. Now we have our thumb pointed in the direction of the electron flow, and our fingers wrap in the direction of the magnetic field. On one side of the wire, the magnetic field goes into the page. On the other side of the wire, the magnetic field comes out of the page. For this example, we have two wires placed parallel to each other with current flowing in opposite directions. We point our thumb in the direction of the current and our fingers wrap to show us the direction of the magnetic field, which is into the page on the left and out of the page on the right. Since the other wire points in the other direction, when we point our thumb in the direction of the current, we find that the magnetic field is the opposite, out of the page on the left and into the page on the right. Since the magnetic field in the region between the wires point the same direction, we know the wires are going to repel. This is because like magnetic fields repel. For another example, we'll have two parallel wires placed next to each other with the current flowing the same direction through the wires. So for the first one, we point our thumb in the direction of the current and our fingers point in the direction of the magnetic field, giving us a magnetic field into the page on the left and out of the page on the right. The second one, the current goes the same way, so we have a matching magnetic field, into the page on the left and out of the page on the right. Since the magnetic fields in the region between the wire are opposite, we know the wires will attract. Because like magnetic fields attract. Part 3. Induced magnetic fields around solenoids. If a current-carrying wire is looped, the magnetic field will spiral around it. So if we have a loop of wire, I'm going to draw the current as electron flow traveling around the wire as shown. If we try the first hand rule by pointing our thumb in the direction of the current, we see that our fingers wrap around the wire, so our fingers come out of the page inside the loop, and they go into the page on the outside of the loop. This continues as you move your hand around the loop, with the magnetic field coming out of the page on the inside of the loop and going into the page on the outside of the loop. The result is that the magnetic field is one direction inside the loop and the other direction outside always. This is magnified if you add more loops. A solenoid is a type of electromagnet that is made from a series of looped wires. It would look something like this in real life, but we'll draw it more like this. The second-hand rule gives us the direction of a magnetic field of a solenoid. For the second-hand rule, you wrap your fingers around the solenoid in the direction of the current. Your thumb points in the direction of the north pole of the electromagnet. So you wrap your fingers in the direction of the current flow in the wire loops. If you're dealing with negative current or electron flow, you use your left hand. If you're dealing with positive current flow or conventional current, you use your right hand. Your thumb points to the north end of the solenoid. Example, will these solenoids attract or repel? We start off by determining the direction of the current flow through the solenoid. I'm going to look at electron flow, which is from negative to positive. So the electrons flow out of the negative side, up through the wire, and as it spirals, it continues to move up through the wire. So to use the second-hand rule, we point our fingers so they wrap around the wire in the direction of the current flow, in this case upwards and around, and our thumb points at the north end of the solenoid. We then look at the other solenoid in our picture. Again, I'm going to go from negative to positive, so we draw in the current, and it wraps around the wire. So in this case, it's always traveling down through the wire. Use the second-hand rule. We curl our fingers so they're traveling down as they wrap around the wire. This puts the north end of the solenoid in the direction our thumb points, which is on the left side of the solenoid. Because we've got two north poles facing each other, we know that these two solenoids will repel. Second example, draw the magnetic field inside and outside the solenoid. Again, to do the second-hand rule, we have to determine which direction the current travels through the solenoid. Again, an electron flow will travel from negative to positive, so the current travels through the solenoid, and as it goes through the wire wraps, it's always traveling down. So we set up our hand so our fingers wrap down around the wire, and our thumb points to the North Pole outside the solenoid. It's important to realize that this is the North Pole outside the solenoid. The magnetic field lines outside the solenoid travel from north to south. But they don't just stop there. The solenoid is hollow. It's a tube with wire wrapping around it. And we know that the looped wire has a magnetic field going the other direction on the inside of the loop. So we continue our magnetic field inside the loop in the direction that it was going from the outside. And we see now the magnetic field lines point the other direction inside, which tells us from the perspective of somebody standing inside the solenoid, the south would be on the left, and the north end of the solenoid from the inside is on the right.